Welcome to the Cosmic Classroom. Today we're going to look at the 2023 IB Physics Paper 1 from November, Time Zone 1. So let's get started. So question 1, we're being asked what the unit of K, the constant, is in this equation. So if we rearrange the equation, we get K is F divided by V. Force is measured in newtons, speed is measured in meters per second. Now at this point, don't get confused and think that the answer is B. The answer is not B. That meters is on the bottom of the fraction, so that would be an m to the minus 1 if it were going to appear in the equation, so it is not B. That is newtons needs converting into base units because Newton second to the minus 1 and Newton ms to the minus 1 both do not match, so we get rid of A and B. Now newtons we convert using the F equals ma equation, so a newton becomes kilogram meters per second squared. Pop that into the expression we had to start with. We had kilograms meters per second squared, meters per second. We're going to lose the meters out of the expression. We've lost the meters out of the expression, that means it can't be C. If we tidy that up, we would see that we would get minus 2 minus minus 1 would become minus 1, and we get kilograms seconds to the minus 1, which is D. Question 2, we've got an acceleration time graph and we're asked to pick the correct velocity time graph. Now the acceleration time graph shows the gradient value of the velocity time graph. So we can see clearly that acceleration is changing throughout the time. That means velocity, the gradient of the velocity time graph must also be changing. It is not a constant gradient, which means it cannot be B or D. These both have constant gradients. If we plotted the acceleration time graph for either of those, gradient of that line is constant, it would just be a constant flat line. D would be a constant negative horizontal line. Also, if we look at the acceleration time graph, the acceleration is always positive. It's never negative, so therefore we can automatically then rule out C. This has negative gradients for its graph, meaning the acceleration would be negative, and we've just got purely positive acceleration, therefore the answer is A. Changing gradient, always a positive gradient. Question 3, we've got a projectile moving in the air. What is the direction of the net force at the point shown? Now the first thing to note here is the shape of the path of the projectile. It is not a perfectly smooth parabola, as we normally see when we talk about projectiles and motion. That's because we normally talk about projectiles when there's no air resistance acting in the horizontal direction. Now, it does not say this in the question. This is something you're expected to be able to interpret from the shape of the projectile's path. There is clearly an air resistance force acting opposite to the direction of motion that is causing the slowing in the horizontal velocity, and this is responsible for the steeper drop in the path at the end in the second half of the motion. So if there is a resultant force to the left horizontally to slow the projectile, cause the steeper descent, we also need to take into account there will also be the weight of the projectile throughout acting down towards the ground. That means that the resultant of those two forces is going to be in direction B of the options that we have been given. Question 4, 2 blocks in contact. A force F is applied to the smaller block M, causes the block to move with an acceleration A. So this is a connected body problem. The 2 blocks are touching, they are one entity, which means that every part of the system has the same acceleration, whether we consider the system as a whole or one of the blocks individually. Okay, so what I'm going to do to start with is I'm just going to write out some expressions for different areas of the system with this idea that F equals ma what's the resultant force on that part of the system? The acceleration is always the same throughout. So first of all, let's consider this as one large system, so just as one block, since they are connected to each other. We have force F acting on that block. It's acting on the system. It's accelerating both of these at an acceleration A. Okay, let me consider just the small block, block M. It is still subject to the force F. There is now, however, a contact force acting on it. The large block, capital M, pushes back on the smaller block with some force. Let's call that F2, just for the sake of argument. It is still moving with acceleration A, because it's a connected body, it's still the same system. So the resultant force here, it's still moving to the right as well. So F is larger than this F2 force, this contact force acting back against the direction of motion from contact from block M. And that's equal to now just little m A. Okay, so there is an expression for the small block. Let's consider then the large block on its own. Newton's third law says that if the large block pushes on the little block with force F2, then the little block pushes back on the larger block with the same force F2. There are no other forces acting on the larger block, only the contact force between the two blocks. And like I said, Newton 3 means that those two forces, F2 is the same on the little block and the larger block. So the resultant force on block M is just F2, and that is equal to its mass, and again it has the same acceleration as every other scenario. Now the question wanted the size of the force that's accelerating the larger block, capital M. Thankfully we have now found that. We haven't had to do any further, we don't need to do any further calculations, it's here. So just by working our way through the system, considering the different parts, we may have had to do more algebra, which is why I went through writing out the different sections, but actually, thankfully, we do not need to do more algebra, and we have found the answer we need. It is B. Next question, question 5. So we've got a block sliding down a slope. This is a classic type of question, inclined plane. We've got a bit of information about the forces. We've got a coefficient of dynamic friction, mu d. We've got the normal reaction force n. It wants to know what the angle of the slope theta is. Notice up at the top here, it's moving at a constant speed, so we're in an equilibrium position in terms of forces. So first thought here is force diagram. What forces do we have acting, and then what can we resolve to get an expression for theta in terms of the variables we've been given. So we have a weight force acting vertically down, mg. We have the normal reaction force n acting up from the plane, and we also have the frictional force acting up the slope opposite the direction of motion, and this is mu d times n. So if we draw that as a free body diagram, we've got the normal reaction force n, we've got the weight force mg, we've got the frictional force mu d n, and then we should be familiar by now with the fact that if we extend the line down from the normal reaction force, that the angle between that and the weight is equal to the angle of the slope. Right? If you're not sure where I've got that from, go back and have a look at your similar triangles. You should be able to move this angle theta up to this angle here. If you're not 100% confident of how that worked, it is something that is worth remembering. I just remember that the angle of the slope is equal to the angle between the line perpendicular to the slope and the weight force acting vertically down. That is equal to theta, the angle of the slope. So we can see here that mg sine theta is balancing the frictional force mu dn, because if we look at all our answers are in terms of the frictional force mu dn. So we've got mg sine theta is equal to mu dn. Remembering we're moving at a constant speed, so the forces are balanced in the horizontal and the vertical direction. That gives us sine theta equals mu dn over mg, and that's going to be, we do the inverse sine of that, it's going to be sine to the minus 1 mu dn over mg, which is answer D. Okay, question 6. We've got an object falling from rest. We've got it in a vacuum, so my immediate thought is there no frictional forces need to be considered, no air resistance, etc. R is the rate of change of the kinetic energy with time. How does R vary with time? So if we think about what's happening here, we're wanting the R is the rate of change of kinetic energy with time, so it's how the kinetic energy is changing with respect to time. It's an object in free fall, so the change in kinetic energy is going to be the change in GPE that's occurring. So it's losing GPE, gaining kinetic energy. So we're looking at M and G are constant. It's going to be the H value, the distance fallen, that is going to change with respect to time. Now we can think about M and G are both constant, so they're not impacting the value of R. We want to know how R is related to T, the time that's passed. And as time passes, the distance through which the object has fallen is going to increase, and that is going to increase quicker and quicker as the speed increases. The object accelerates on its way down towards the ground. It's going to be covering a larger and larger distance each second as it accelerates. So the question is, how does H vary with time as the object falls? Now we can do this with a suvat, so we can do S is our distance fallen, U, it's falling from rest, if we go back and read the question, so it starts at rest. The final speed doesn't matter, we just want to know how H changes with respect to time, and the acceleration is equal to gravitational field strength. There's just the force of gravity, just the weight acting down, accelerating it, and then time is just the amount of time that has passed. So the suvat we're going to go for there is going to be the S equals ut plus a half at squared expression. So H, the distance travelled, the distance that's been fallen with respect to time, is equal to U is 0, so ut disappears. It's equal to half gt squared. Now if we take this expression and put it back in here, we can then see how R varies with respect to t time. So R is mg, H is then a half gt squared, and we're doing this with respect to time. So we're going to see the t squared on the top is going to cancel with the t on the bottom, two g's on the top, so we're going to get g squared, so we're going to get R equals a half mg squared t, and then from that we can see R is proportional to t because the half, the m and the g are all constants. R is proportional to t, which is a linear relationship, which gives us graph A. Another kinetic energy question, but this is a ratio question, so you get lots of these on paper 1. So we want to know the momentum of one object with respect to the momentum of the other object, and we're given a variety of different information about how the two momentums are related. So we've got the x has a mass that is twice the mass of y, the kinetic energy of x is 4 times that of y, what's the value of momentum of x with momentum of y? So if you go into your data booklet, there is an expression that relates momentum and kinetic energy, so you should always go and have a check in your data booklet for your equations. So this is EK, so the kinetic energy is equal to p squared, the momentum squared, over 2 times the mass of the object. So if I rearrange that, I get that P for particle x, or object x, is equal to the square root of the energy for x multiplied by 2 times the mass of x, and I get the momentum of y is equal to square root of energy of y 2 times the mass of y. Now I need to kind of get these in the same algebraic terms, so I'm told the values of x in terms of the values of y, so I can change this expression so that everything's in terms of the energy of y and the mass of y. So that gives us the kinetic energy of x is 4 times the kinetic energy of y, and the mass of x is twice the mass of y, which gives us square root of 8 EY to my. And if I do momentum of x over momentum of y, that is square root 8, so this is momentum of x with respect to momentum of y, square root of 8, the energy of y, to my over square root energy of y to my. So obviously you can see that the square root of EY to my, that's all cancelling. We're just being left with the square root of 8, which is 2 root 2. Question 8. So a temperature time graph, you can see we've got some phase changes going on here with the horizontal sections. Energy supplied at a constant rate to a fixed mass of substance. Graph shows variation of temperature with time. Which statement about the substance is correct? So specific heat latent vaporization, specific latent heat of fusion, fusion vaporization, and then some specific heat capacity statements as well. So if we have a look at the graph, we've got 2 phase changes. So we've got solid, liquid, and gas, and then we've got the 2 phase changes. If we think about the definitions of specific latent heat, fusion vaporization, and specific heat capacity, the lower the specific heat capacity, the easier or the less energy it will require to increase the temperature of that substance. So if we look at the solid, liquid, gas phase, the gradient here, if the gradient is steeper during one of these phases, that means that the specific heat capacity is lower. It's requiring less energy, therefore taking less time to gather that energy in order to increase the temperature of the substance. So steeper gradient means a lower specific heat capacity. And then we can see that the power, therefore the energy delivered per second, is remaining constant throughout this period of time. It's taking longer for the vaporization to occur than it is for the melting to occur. Therefore, the specific latent heat of vaporization, it must be larger than the specific latent heat of fusion. It's taking longer to gather the necessary energy, to deliver the necessary energy to convert from a liquid to a gas, than it is to convert from a solid to a liquid here. That's taking less time, therefore the latent heat of fusion is lower than the latent heat of vaporization. So let's have a look at the statements, see which one we agree with. The specific latent heat of vaporization is greater than the specific latent heat of fusion. Well, yes, we have just said that's true, so I think it's probably going to be A, but just let's check B, C, D to check we're happy that the others are indeed incorrect. Latent heat of fusion is bigger than vaporization. No, that's the wrong way around. Specific heat capacity of the solid is greater than the specific heat capacity of the liquid. No, because remember, steeper gradient means a lower specific heat capacity, so the solid actually has a steeper gradient than the liquid, so the specific heat capacity of the solid is less than the specific heat capacity of the liquid. And then lastly, specific heat capacity of the vapour is greater than the specific heat capacity of the liquid. No, same argument, the gradient is steeper for the gas, for the vapour, than it is for the liquid, meaning its specific heat capacity is lower, so it is indeed A, the first option. Question 9. Fixed mass of an ideal gas, the pressure is proportional to variety of options. So first thought is ideal gas pressure PV equals nRT. Or we're interested in what pressure is proportional to, so pressure equals nRT over V. So pressure is definitely proportional to temperature, so it is not going to be A. So we've got temperature in B, C and D. Proportional to absolute temperature and volume. No, it's proportional to 1 over volume, so it's not A. It is not C. Density and absolute temperature, or absolute temperature only. Well, it's not just absolute temperature only. We've definitely got a volume element, and volume is linked to density. In fact, what we've got here is nRT, and we've got 1 over V. Now, 1 over V is proportional to density for a fixed mass of gas. Remember, density is mass over volume. So if mass is a constant, density is proportional to 1 over V. So we could replace 1 over V with density. So the answer is B. Question 10, number of atoms of a sample of neon versus number of atoms of a sample of krypton. So number of atoms is equal to all the n's, little n, times Avogadro's number. And the number of moles, little n, is the mass over the molar mass. So if we do this for the neon, we get 20 over 20, so 20 grams, that's neon 20, times Na. And if we do that for the krypton, we get it is 40 grams and krypton 80 Na, and then it is a division, so we're doing the neon over the krypton. So the 2020, that's just 1, so we're doing Na, and then we've got the 40 over 80 Na on the bottom. The Na's are going to go, we've got a fraction on the bottom of a fraction, that's going to flip and multiply, so it's going to be 80 over 40, which is 2, so C. Question 11, we're into the waves topic now. Wave is travelling on a string. We've got a graph showing displacement with distance and displacement with time. We want to work out what the speed of the wave is, so we want to do, ideally, a V equals F lambda. Now, from the first graph, displacement with distance, we can get the wavelength. So displacement with distance, there is our lambda. So lambda is 4 centimetres. Then displacement with time, we can get, not the frequency, but we can get the time period. And since we know that F is 1 over t, we can use that in place of F in the wave speed equation. So we can get the time period on this one. So the time period is 2 seconds from this second graph. So we get V equals 1 over the 2 seconds multiplied by, all the answers are in centimetres per second, so no need to convert, multiplied by the 4, that is 2 centimetres per second, which is A. Question 12. Polarisation question. Unpolarised light of intensity I0 is incident on a polariser with a vertical axis of polarisation. So we've got I0 incident on a vertical polariser. The transmitted intensity of this polariser is I1, so we get I1 out of that first vertical polarizer. The light is then incident on a second polarizer with a vertical axis of polarization. So we then hit another polarizer. The transmitted intensity is I2. What are I1 and I2? So the equation for this, we're looking at our data booklet, the transmitted intensity is equal to I0 cos squared theta, where theta is the angle of the polarizer. So initially I0 is unpolarized, so we have light in all directions initially before we're then incident on the polarizer. Now, bit of knowledge you should have, and if you don't, this is me telling you this is something you should know. When we have unpolarized light and it passes through a polarizer, look the maths up online if you want, what happens is we get I transmitted becomes equal to I0 over 2. We get half of the light transmitted through the polarizer. This is to do with vectors and the fact that if it's somewhere in between, like the 0 and the 90 degrees, there is a component of the light that is transmitted through the polarizer, and when you end up summing up over the full 360, you end up getting half the light being transmitted. You can look that up online for the proof if you're interested, but if you don't, it's at least a little bit of knowledge you should have. It's something that you should remember. Unpolarized through a polarizer in one direction, half of the light gets transmitted. So I1 is I0 over 2, so automatically lose C and D. We definitely lose some of the light. Then I1 is already all polarized in the vertical direction. So then when it meets a second vertical polarizer, we're not going to lose anything. All of it is going to pass through from I1 to I2. So I2 is going to be the same as I1. We're not going to lose any more of the light. Polarizers are in the same direction. Therefore, the answer is B. We get half through the first polarizer. Direction of polarization is exactly the same for the second polarizer, so we lose no more of the intensity. We get the same out through the second polarizer. Question 13, refraction question. Medium 1, medium 2, so medium 1 has a refractive index N1, medium 2 has a refractive index N2. Wavelength in medium 1 is lambda 1, wavelength medium 2 is lambda 2. What is correct for the comparison of the refracted indices and the wavelengths? So we can see here we've got the ray of light moving towards the normal. That means that the ray of light has slowed down as it's gone into medium 2. That means that the refractive index of medium 2 must be larger than the refractive index of medium 1. So we can lose A and B. And then if it slows down, the wavelengths become more compressed. So the wavelength gets closer together as it slows in order to maintain the same frequency. Therefore, the wavelength in medium 1 is larger than the wavelength in medium 2. Question 14, standing waves. Standing sound wave is established in a tube, one end open and one end closed. So, sketch time. The first harmonic. So our first harmonic, node at the closed end, antinode at the open end, length of the pipe. When the length of the tube is increased by 0.1 meters, the next harmonic is formed. Okay, second harmonic, we add a node. So now we've got an extra node in the middle, still got the one node at the end, still an antinode at the opening. And now the length of this pipe is the original length plus an extra 0.1 meters. So we asked the wavelength of the sound wave. So in the first harmonic, the length of that pipe is equal to a quarter of the total wavelength. We've got a quarter of the wave visible there. In the second scenario, we've now got the length of the pipe plus 0.1 is equal to 3/4 of the full wavelength. Now we can substitute in for L in this second expression, and we can calculate a value for lambda. So a quarter of lambda plus 0.1 equals 3/4 of lambda. 0.1 is 2/4 lambda, or half the wavelength. Therefore, the wavelength is going to be c, 0.2 meters. Question 15, 2-point charges plus 4q minus q placed a fixed distance apart. Where is the electric field strength equal to 0? Alright, so we need to think about the directions in which the electric field strength is acting to start with, and which charge is responsible for the electric field strength. Remember, the electric field strength decreases with distance. So and it points in the direction that a positively charged particle would move if it were placed at that spot. So at A, the plus 4q charge would be repelling a positively charged particle. The negative charge would be attracting one. At B, the plus 4q would still be repelling. The negative would still be attracting. At C, plus 4q is repelling, but now in the opposite direction. Minus q is attracting. And at D, the plus 4q charge is repelling. The minus q charge is attracting. So we're looking for a point where E is equal to 0, so we can automatically rule out C. Both the fields are pointing in the same direction at C, so therefore they're not going to be cancelling out. Electric field strength, because we've got this inversely proportional relationship with distance, the electric field strength is going to drop off with a 1/r² relationship. So if you look in your data booklet, you'll see that electric field strength E is equal to F/Q, and you should remember F is K Q1 Q2 over r². Therefore E is proportional to 1/r². So as the distance doubled, the field strength quarters. So because we've got quite a disparity in the size of the two charges, the 4q and the q, we need to be pretty close to the minus q and further away from the plus 4q in order for the two field strengths to have the opportunity to be the same size. So the minus q we need to be closer to, and the 4q we need to be further away from. The only place where that happens is D. So the field strength from the minus q will have decreased a little bit, but not too much, whereas the field strength from the plus 4q will have decreased much more at that point, and there is the possibility that they could be equal to each other. On the other side, we're much closer to the 4q than we are the minus q, so that's not going to work in terms of their field strengths being the same size to cancel out. The 4q is going to be much larger than the minus q because we're closer to it, and much further than the minus q. Therefore, D is the only place where they have the possibility of being equal and opposite, further from the larger charge, closer to the smaller charge. Question 16, resistivity question, copper cylinder, diameter D, length L, resistance R. What is the resistance with the diameter 2D and length 2L? Now this is a classic, change a couple of variables, how does the outcome change? To approach these, I always do the same thing. I write an initial algebraic expression for the initial parameters. I then write a new algebraic expression for the new parameters, and I try to factorize out my original expression to leave then a multiplying factor just at the front in terms of, is it twice as big, half as big, root 2 as large, etc. So let me show you what that looks like. So resistivity and resistance expression. So resistance is resistivity times length over area. We're dealing with diameters here. So area is pi d over 2 squared is our area that we're dealing with. So our initial resistance, so the initial parameters with diameter d and length l is rho l over pi d over 2 squared. Let's simplify that because that is a bit messy. That's coming out at 4 rho l over pi d squared. So that is my initial expression. So I'm now going to do the same thing but for the new parameters 2d and 2l, and then I'm going to try and find this expression within that one, pull it out, factorise it out, and look at what multiplying factor I'm left at the front of the expression. So now my new resistance is rho l over, and now we're on pi 2d over 2 squared. So the 2 over 2 is going to cancel on the bottom. So I've got rho rho l over pi d squared. Now I'm trying to find a 4 rho l over pi d squared. So if I'm going to make this equal to 4 pi l over rho d squared, I'm going to have to add a multiplying factor of a half. So that is a half times 4 rho l over pi d squared. There is my original expression for r, multiply it by a half, and I'm getting 2 rho l over pi d squared. So therefore my new resistance is equal to half of the original resistance. So B. Question 17. 3 particles, identical magnitude of charge, different mass, entering uniform magnetic field, same initial velocity, magnetic field directed into the plane of the paper. What is the mass of particle X compared with the others? What is the sign of the charge on particle X? So a couple of things here. One is Fleming's left-hand rule, which is going to allow us to know the sign of the charge because that will give us current direction, and we can see if particle X is moving in the direction of positive charge current or moving in the direction of negative charge. Mass in comparison, that's related to the radius of the orbit. So the force acting on the charge is given by BQV. The force is the centripetal force, mv squared over r is BQV. Rearranging that gives us that the radius of the orbit is equal to the mass times the velocity over the field strength times the charge. So we're told that they have the same initial velocity, so v is the same, they're in the same field, they have the same magnitude of charge, so the only difference is the mass. So the larger the mass, the larger the radius of the orbit. Particle X has the largest radius of orbit, therefore it has the largest mass. Therefore C and D can go straight away, and we just need to determine whether particle X is positive or negative. The direction of the force is in towards the centre of the circular path at any point, since it is a centripetal force, so pick a point along the curve. Fleming's left-hand rule, fingers out, so first finger into the page for the magnetic field, thumb pointing in the direction of the force, and you should find that your middle finger pointing in the direction of current will be going this way. Now, current is positive to negative, it's the direction positive charge would flow. Particle X is moving in the opposite direction, that means it is negatively charged, so it is B. Question 18, we are looking at the difference in gravitational field strength. What's the gravitational field strength on the surface of planet X compared to that on the surface of the Earth? So gravitational field strength on the Earth is G, mass of the Earth, over the radius of the Earth squared. We're then told planet X that the mass is 300 times as large, and we're told that the radius is 10 times the radius of the Earth. That all gets squared, so we're going to end up with 300 over 100 multiplied by G, mass of the Earth, over radius of the Earth squared. That is G for the Earth. Therefore, for planet X, it is 3 times the size of the Earth's gravitational field, so C. Question 19. We've got 4 times 10 to the 22 atoms of a radioactive isotope. Got a half-life of 15 seconds. How many atoms remain after 1 minute? So this is a basic half-life question. Definition of half-life: number of radioactive atoms halves during the time it takes for one half-life to pass. So we start with 4 times 10 to the 22 atoms. After 15 seconds, we've then got 2 times 10 to the 22. After another 15 seconds, we've got 1. Then we've got 0.5. And then we've got 0.25, and that is our 1 minute. 15 seconds, 30 seconds, 45 seconds, 60 seconds. There is our 1 minute. We've had 4 half-lives in our 1 minute. So we've got 0.25 times 10 to the 22 radioactive atoms remaining, or 2.5 times 10 to the 21. A pi plus meson can decay in the following way. What is correct for particle X in terms of what particle should it be, and what's the exchange particle for this interaction? So we have a meson at the start, so we're looking at conservation rules. A mu plus is a lepton, specifically it is an anti-lepton, because mu minus, the muon, is the lepton. This is a positive muon or an anti-muon. It's an anti-lepton. So since we had no leptons initially, and then we've gone to a lepton, we have an anti-lepton, and therefore we need a normal lepton for X in order to cancel out the lepton number and give us a lepton number of 0. If you can't remember what numbers everything has, if you go to your data booklet, subtopic 7.3, you've got the tables with all the lepton numbers in. So it says leptons have a lepton number of 1, anti-leptons have a lepton number of -1, so that has a lepton number of -1, so we need a normal lepton with a lepton number of +1. So we need a neutrino, which is going to be A or B, so it is not C or D. Then in terms of the exchange particle, we have a positive charge at the start and a positive charge at the end. That positive charge is being carried through from the meson to the muon. So therefore it's going to be a W plus particle. It's carrying the positive charge through. So it is A. Which of the following is not considered to be a greenhouse gas? This is a knowledge question. So N2O and CH4, we should be perfectly happy that they are indeed greenhouse gases. The one that might catch you out is H2O. H2O is also a greenhouse gas. Remember, water has a very large specific heat capacity. It holds on to a lot of thermal energy. So C, oxygen, is not a greenhouse gas. Question 22. Black body, temperature T Kelvin, peak wavelength lambda. What is the peak wavelength when the temperature increases by 33%? So this is Bean's law. Lambda max times temperature in Kelvin is equal to a constant. And then we increase the temperature by 33%. So the new lambda max is the same constant, but then the temperature was 1T, and then we've added another 33%, so we've added another third onto that. So the new temperature is now 4/3T compared to the original T. It is 1/3 larger. So that is 4/3T. That's fraction on the bottom of the fraction, so that 4/3 is going to flip and multiply, become a 3/4, and the answer will be B. Particle is executing SHM. Total energy E, amplitude x0. What is the kinetic energy of the particle when the displacement from the equilibrium position is x0/2? So if you go to your data booklet, you'll see that the kinetic energy expression is a half m omega squared x0 squared minus x squared. Okay, so let's put in x0/2 for the x squared. So half m omega squared x0 squared minus, and now it is x0/2 all squared. Expanding that, that becomes half m omega squared x0 squared minus, and it's still a half m omega squared, but now it's x0 squared over 4. Now, if you also have a look in the data booklet, this expression here is the expression for the total energy, and we have that in both of these. We also have the half, the m, the omega squared, and the x0 on this side. We just have an extra quarter on this right hand side to deal with for the divided by 4 on the x0 squared. So we can simplify this expression to EK equals the total energy, and then we've got minus, so we've got the total energy expression again, we've just got a quarter of it, so minus a quarter of the total energy. So the kinetic energy is equal to 3/4, so the total minus a quarter, so it's 3/4 of the total energy. Question 24. Interference pattern intensity, 4 slits. What change occurs when the number of slits is increased, but the separation of the slits and the widths of the slits does not change? Okay. The width of the primary maxima decreases, position of the primary maxima changes, number of secondary maxima decreases, intensity of secondary maxima increases. So, couple we can get rid of straight away. The position of the primary maxima changes, well, that's not going to change. We're always going to have the maxima along the central line in the middle. Number of secondary maxima decreases. Well, that's not going to happen either. We're going to have more slits, which means the number of maxima that we're going to see is going to increase, not decrease. The intensity of the secondary maxima increases. Well, that is not going to happen either. We're not going to have brighter light shining through more slits as we kind of increase the slit number. We're not going to see those outer bright fringes, those maxima getting brighter as we have more slits for the light to go through. But the width of the primary maxima will decrease, and this is because if we think about our patterns that we see when we have multiple slits, I'll just do like the single to second, 1 slit to 2 slits as the initial example, and then we can discuss how that would change with more and more slits we add. So if we remember our diffraction pattern for a single slit, it kind of looked like this: large central maxima, smaller secondary maxima. But then when we did 2 slits, we saw the pattern for the 2 slits sits inside the pattern of the single slit. And all that's going to happen is as we add more slits, the pattern inside changes slightly, but we still get the bright and the dark fringes. As we add more slits, we're just going to get more and more maxima within this central envelope, and the only way we're going to get that is by narrowing these maxima widths. These are going to have to get narrower to accommodate the greater number of maxima within the single slit envelope. So the answer is going to be A. Diffraction grating. We're resolving two spectral lines. We've got the mean wavelength difference. What's the minimum order at which the diffraction grating can resolve? So go to the data booklet, and we want this expression. The resolvance is lambda over delta lambda equals m times n. Right, so m is the number of, it's the order, the minimum order at which it can resolve. Lambda is our mean wavelength, delta lambda is the difference in the wavelength, n is the number of slits. Okay, so we're rearranging to find m, essentially. So we've got 500 over 0.05. Don't need to worry about unit conversions of the same unit, and it's a division. Trying to find m, and the number of slits is 6,000. So we've got 10,000 equals m over 6,000. So when we do 10,000 divided by 6,000, we're going to get an answer somewhere between 1 and 2. It's more than 1, it's less than 2. So m is sitting between 1 and 2. So it cannot resolve the first order. It cannot resolve the first order. The minimum order it can resolve is larger than 1. It cannot resolve the first order, but it is less than 2. So the second order is going to be the first, the lowest, the minimum order at which that diffraction grating can resolve those two lines. Siren emits a sound. Wavelength lambda, speed c when it's at rest. It then moves. What's the wavelength and speed of the sound received by the observer? So stationary observer, moving source. So we've got Doppler effect going on. So it's stationary observer, moving source. So the expression from our data book is this one. The new frequency is equal to f multiplied by speed of the wave over speed of the wave, and that's going to be plus or minus the speed of the source. Okay. Now, in this case, the siren's moving towards the observer. That means that the pitch they're going to experience is going to be of a higher frequency if the source of the wave is coming towards them. So that means that f dash needs to be larger than f, and we're going to get that if we have a smaller denominator on the bottom of the fraction to give us a larger answer. So therefore this is going to be a v minus us that we're going to need rather than the plus. Now the tricky bit with this question is that they've given us lots of symbols that represent different things just to try and confuse us. Okay, so the siren emits a sound of wavelength lambda and speed c. So the speed of the wave, the speed of the sound wave, v, is, according to the question, c. So it's not, they're using the speed of light symbol just to try and confuse us, but it's just the speed of the sound wave, we're giving the symbol c. And the speed of the source, the siren moves towards them at speed v, so the speed of the source is v in this expression. We are trying to work out the wavelength alongside the speed. So one thing we can do is we can get rid of a couple of answers straight away. The speed of the wave does not change. It's still moving through the same medium. It is still moving through air. Therefore, the speed of the sound remains constant. It was originally c. The speed of the sound is still c. It is still moving through air. We've not changed that. The speed of the sound wave remains constant. So it's A or B, not C or D. We then need to work out how the wavelength is changing. So obviously the wavelength is changing, the frequency is changing, the wavelength is changing, the speed of the sound stays constant. So we can do this algebraically, which I'll do in a second, but we can reason the answer without having to do the algebra. So if the speed of the sound is fixed, but we know that the frequency appears to have increased because the object, the siren, is coming towards us, then that means that the wavelength must drop. It must decrease in order for the speed of the sound wave to remain constant. Now, to me, that automatically looks like it should probably be B. We've got a 1 minus V over C, so we've got like the original lambda minus a new fraction of lambda, and that's going to give us a definitely smaller wavelength. Let's double check for A. Speed of these V is much less than C. Okay, so it could still be A. V is a smaller number than C, so that does give us a smaller fraction of lambda. Okay, not quite worked out. Thought we might have been able to reason. No, we're going to need to do the algebra, so let's do the algebra. So we know that frequency, so the original frequency, F, or the frequency of the source, is C over lambda, and the observed frequency is C over the observed wavelength. Like, so if we look at our expression for wavelength, well, it's wavelength, we need to get rid of the frequency term, that's the easiest way to do so. So let's sub that into the Doppler effect equation. So we get C over the observed wavelength is C over the emitted wavelength. Now let's swap our V's and V minus US's for our terms that are given in the equation, being careful not to get ourselves jumbled up with the terms. The speed of the source is C. Sorry, the speed of the wave is C. Speed of the wave is C. Speed of the source is V. I want to know what lambda is. At the moment, lambda's on the bottom of our fraction, but it's fractions everywhere, so let's flip all the fractions. So flip all the fractions. C minus V over C. These two C's are going to cancel. If I multiply by this one up on this side, it's going to cancel out with the lambda on the bottom of that fraction. I now have the observed wavelength is equal to the emitted wavelength multiplied by C minus V over C. That C minus V over C will expand, well, separate out. It's a C over C minus a V over C, or a 1 minus V over C, so the answer is B. We've got a point charge Q located at position X. Two other points, Y and Z, are positioned such that Y to Z is 2 times X to Y. So if X to Y is a distance R, then Y to Z is twice that distance, that's the distance 2R. What is the electric field at Y versus the electric field at Z? Well, Z is a distance then of 3R away from the charge Q. Electric field is KQ over R squared. So the electric field at X, sorry, not at X, at Y, sorry, we were after the electric field at Y is just KQ over R squared. The electric field at Z is KQ over 3R all squared, careful with that, so it is KQ over 9R squared. Now if we do Z, oh no, wrong way round, X, not even X, Y, read the question properly, Y over Z, KQ over R squared, KQ over 9R squared, KQ over R squared, flip and multiply by the fraction on the bottom, 9R squared over KQ, so everything's going to cancel apart from the 9, the answer is D. Question 28. Two parallel plates, equal and opposite charges. The potential on X is Vx, the potential on Y is Vy. Where Vx is larger than Vy, so if Vx is larger potential, that makes it the positive plate, and that makes Vy then the negative plate. It has the lower potential. A point particle of positive charge Q and mass m. Positive charge Q is held at rest midway between the plates. Particles released. Which plate will the particle move toward, and what kinetic energy does it have when it reaches the plate? So, easy bit first, which plate is going to move towards? It's a positive charge. It's going to move towards the negative plate, so it's going towards Y. So it's not A or B. What's the kinetic energy when it reaches the plate? So the energy that the charge receives is going to come from the energy it receives from the difference in potential. So this expression, E equals Q delta V. Right, so the energy it receives, which is going to be its kinetic energy, is going to come from the potential difference, delta V. Now, Q, because it's held in the middle, is only going to move half the distance between X and Y. Therefore, it's only going to move through half the total potential difference. So the energy it receives is going to be Q. The potential difference is Vx minus Vy. But the charge is only moving half the distance between the two plates, so it only receives half that potential difference. So Vx minus Vy over 2, the answer is D. Question 29, we've got a hollow sphere. We're at position point P inside the sphere, distance r over 2 from the centre. What are the electric potential and the electric field at point P? So this is a hollow sphere, positive charge Q. So that positive charge is sitting all around on the surface of the sphere. And the first thing we can do is think about the electric field inside the sphere. So the electric field is in the direction that a positive charge would move, but since this is a circle, for all these positive charges, if you take lots of tiny individual positive charges on the outside of the sphere, the electric field from any point on the outside of the sphere, when it comes to the interior, is acting in towards the centre. And we're going to find that they're going to cancel each other out. This one is going to take this one out, this one's going to take one down here out, and so on and so on and so on. And actually what we'll find is that the interior of the sphere has an electric field of 0 because of this circular nature. None of the charge is held inside the sphere, it's all on the surface. All of the electric fields are pointing in equal and opposite directions at every point. So the electric field inside is 0. So we can get rid of A and C for that. So now we're just after the electric potential. So the electric potential on the surface, where the charge is being held, the electric potential on the surface is equal to KQ divided by R. That's the equation for electric potential, KQ over R. Now, what's the electric potential at point P? Now this also links to the field. So since the field inside the sphere is constant, it has a constant value of 0, there is no change in potential when moving inside the sphere. You're not moving through a changing electric field. There is no change in the field strength. If there's no change in the field strength, there is no energy, no work necessary to be done to move around inside the sphere. And if there's no work being done, there's no change in potential between the 2 points. So that means that the potential inside the sphere is constant. It does not change. So the potential inside the sphere is equal to the potential on the surface of the sphere, so that when we move through the interior of the sphere, there is no change in potential because the field is zero. So the potential inside the sphere is the same as the potential on the surface and is equal to kq over r. Satellite orbit. The total energy of the satellite is minus gmm over 4r. What is the radius of the orbit? So the total energy when in orbit, if we have an expression, so we've got the total energy is gmm over 4r. But if we think about the total energy at the planetary radius versus the total energy at the orbital radius, the total energy at the planetary radius is the potential energy plus the kinetic energy, which is minus gmm over r plus a half. That's the radius of the planet, plus a half mv squared. And from our data booklet, we can change the v squared from one of our orbital equations. We can change that, so it's minus gm our planet plus a half g our planet, which gives us a total energy if we were on the surface of the planet and just, moving around with its rotation, of minus g over 2 times the radius of the planet. Now the total energy of the satellite is minus g over 4, and that's the radius of the orbit of the satellite. Hopefully we can ignore the negatives, the g, the m's, and the m's are all going to cancel out. And we're going to get left with 1 over 4 times the radius of the orbit is equal to 1 over 2 times the radius of the planet. I want the orbit radius in terms of the planet radius. So we're going to end up with the orbit radius over the planet radius being 4 over 2, or it's going to be twice the planetary radius is the radius of the orbit. Question 31 is to do with root mean squared current and power in an AC circuit. So we're told we've got a direct current of 4 amps dissipating a certain power P, and then we've got an AC current dissipating the same average power through the same resistor. What is the value of the RMS current in the AC circuit? So for our direct current circuit, we've got the power is I squared over R, is 4 squared over R. And then in our AC circuit, we have the average power is now the RMS current squared over R. So we just change the power for average power in an AC circuit, we change the current for the RMS current in the AC circuit. These two are the same, they're equal to each other, so that makes 4 squared over R equal to I RMS squared over R. The R's are going to cancel. I RMS squared is going to equal 4 squared, so the RMS current is also going to be 4 amps. It is the same. Question 32, we've got a conducting ring dropped into a magnetic field. What is correct about the acceleration? So this is Faraday and Lenz's law. So if you think about both of those things, when there is a change in magnetic flux, a current is induced in a conductor. So as this ring drops into the field is going to go from having no magnetic field inside of it to then there being a magnetic field inside of it. It's going to be change of flux. Current's going to be induced in the ring. And then Lenz's law says that the direction of that current will be such that it produces an electromagnetic field which tries to prevent the change that caused the current that caused the field in the first place. So the ring is falling into the field. That is the change that generated the current, that induced the current, that then induced the electromagnetic field. So the direction of that electromagnetic field is going to be trying to resist that change, according to Lenz. So that means that the electromagnetic field is going to create a force that is going to repel the motion of the rod into the magnetic field in the first place. So that means that's going to slow it. You're going to have its weight acting down, but then you're going to have this repulsive force from the two magnetic fields. So as it enters, its acceleration is going to be less than g. The induced current and the induced electromagnetic field try to prevent it from falling and entering the magnetic field. So A and B can go, it's C or D. But then as it leaves, we have the same issue. It's still falling. It did have a constant magnetic flux through it. It was inside the field, there was a magnetic field inside the ring. Now the change that is occurring is that it is leaving the magnetic field. It's going from having a magnetic field inside of it to not having a magnetic field inside of it. That again is going to cause a change in flux, which is going to induce a current, and again that current direction is going to generate an electromagnetic field that opposes the change that created it in the first place, Lenz's law. So now the change that created it is that it is leaving the magnetic field. So the electromagnetic field generated by the ring is now going to try and attract it back into the magnetic field. It's going to try and prevent it from leaving. So again, we've got the weight force acting down. We've now got an attractive force from the electromagnetic field of the ring pulling back on the magnetic field that already existed. And that is also going to slow the motion of the ring. It's going to try and keep it inside the magnetic field. So again, the acceleration is going to be less than just g. It's being slowed. Lenz's law doesn't want it to leave the magnetic field. It wants it to stay. So the answer is D. It's slowed on entry and slowed on exit. Both of those are a change in magnetic flux, and Lenz's law basically says that it opposes that change. It opposes it entering, so it tries to stop it from entering. It opposes it from leaving, so it tries to stop it from leaving. Question 33. Got some parallel plate capacitors. Which has the greatest capacitance? Right, so let's look at the capacitance equation. The capacitance equation is the epsilon, the dielectric, A over D. So A is the area, D is the separation. So to maximize the capacitance, we want A to be large and we want D to be small in order to maximize our capacitance C when we've got the same dielectric in between. So the one that maximizes that the best is A. It has the largest area and the smallest separation kind of together. Question 34, we then have a fully charged capacitor. There's just air in between the two plates initially, connected to a voltmeter. Paper is then inserted between the plates, and what is the change in the charge and what is the change in potential difference? There's no change in the charge. It has already been charged, so it is already a fully charged capacitor. We're not charging it anymore, so the charge remains the same. It is already fully charged. C and D can go. Then we're after what happens to the potential difference across the plates. So if we think about the equation, the potential difference is Q over C for a capacitor. Now the charge is the same. The capacitance, however, will have changed with the introduction of the paper. It is a dielectric. It will have increased the value of epsilon in this equation. which means the capacitance will have increased, and if the capacitance has gone up on the bottom of this fraction, but the charge has remained the same, that means the potential difference is going to drop. So the answer is B. Fully charged capacitor, question 35, then discharges through a resistor. We've got the time constant of the circuit is tau. The initial energy stored is E. What is the energy stored at a time t equals to tau? So the initial energy stored is equal to a half C times the kind of initial V0, the initial potential difference across the capacitor squared. Now it is V that's going to vary with time, and that's going to vary by this expression, V equals V0 e to the minus t over tau. And that's straight out of our data booklet for our capacitor. We're doing this at a time equal to tau, the time constant. So V is going to be V0 e to the minus, and we've got tau over tau, so it's V0 e to the minus 1. So after our period of time, so E at time tau is going to be a half C now times V0 e to the minus 1, because that is what V now is. So we sub that in for our V squared. Let's just expand that out slightly. Half C, we've still got V0 squared, and we've got e to the minus 2. This is our initial energy that was stored. So this expression is now our initial energy multiplied by e to the minus 2, which is the same as saying it's the initial energy over e squared, and that is D. Question 36 is a photoelectric effect question. It says light falls on a metallic surface whose threshold frequency is F0. Which graph shows how the current emitted depends on the frequency, and we're told that the number of photons incident per second is constant. So we should already be comfortable with basic knowledge. No photoelectrons are going to be emitted from the surface below the threshold frequency, so there's going to be no current registered below F0. So C and D are out. Current is 0 below F0. Question is then, is the current constant above F0, which is A, or does the current increase above F0, which is I? Now the thing to remember here is that this is a one-to-one interaction. One photon liberates one electron. The number of photons per second is constant. So the number of electrons emitted per second is constant, meaning the current will be constant. Even if we increase the frequency, the number of photons stays the same, so there's still the same number of electrons emitted, so the answer is A. Bohr model for the hydrogen atom. What is the angular momentum of the first excited state, the angular momentum of the ground state? So the ground state is the n equals 1 state, the first excited state is the n equals 2 state. Now this is, again, from our data booklet. This is this expression, so this is subtopic 12.1. This is mvr equals nh over 2 pi. Now mvr is the angular momentum, which is given symbol L. Don't need to worry if you don't know that, but mvr is the angular momentum. H is Planck's constant, 2 pi is constant, so L is basically proportional to n, the state. So we're doing first excited state over ground state, so we're doing L of the L of the excited state over L of the ground state is 2 over 1 is 2. Answer is C. Question 38, we've got an alpha particle is emitted even though its kinetic energy is smaller than the height of the nuclear potential barrier. What makes alpha decay possible? Well, it doesn't have enough energy for it to occur. Height of the nuclear potential barrier, we should be thinking about potential wells The alpha particle's sitting down here, it doesn't have enough energy to get up and out. How do we do that? Well, particles behave like waves, and it can do a bit of quantum tunneling with the wave function, and if its probability wave extends outside of the well, there is a small probability of finding it at a position outside of the well, and we can quantum tunnel our way out using the wave function extending outside of the nucleus, d. In beta decay, the energy of the emitted particles is continuous. This is explained by, this is a knowledge question. This is something you should know. Beta decay, the continuous energies are explained by the existence of the neutrino. The energy is shared between the electron or the positron and the neutrino or antineutrino, and that can be kind of in any ratio, allowing for a range of values for the energy of the emitted beta particle. That's nothing to do with the mass of the alpha particles. Gamma ray emission is linked to evidence for the energy levels in the nucleus, but it's not linked to beta decay. Rutherford scattering experiments. Deviations from the expected results for the Rutherford scattering. Which statements are correct? They provide existence for the strong nuclear force. They allow for an estimation of the radius of the nucleus. They occur when alpha particles are instant at low energies. So, deviations from Rutherford scattering only occur for very high energy alpha particles. So again, this is kind of a knowledge question. They only occur for very high energy alpha particles, the alpha particles that get particularly close to the nucleus. And the thing that is responsible then for those deviations, because they've come so close to the nucleus, it is the strong nuclear force is responsible for those deviations. So 1 is correct. Allows for an estimation of the radius of the nucleus. That is also correct. We're getting our alpha particles close to the nucleus. We can see when these deviations occur. We can make an estimate of the radius of the nucleus. Occurs when alpha particles are instant at low energies. No, we need high energy alpha particles to get close to the nucleus. Remember, the strong nuclear force only has a very short range. It's at that point that we start to see the deviations in the expected results. So 1 and 2 are correct. 3 is incorrect, and we have reached the end of the paper. Hope your time in the cosmic classroom today has been useful, and good luck with all of your revision.